Ever wondered how to design a horn speaker from scratch step by step? With real acoustic data and a full 3D model you can build? Whether you're a beginner or just curious how horns really work, this one's for you. Let's get started. Hi, and welcome to my channel. To get started, go to the website shown on screen. At first glance, you might feel overwhelmed by all the letters and numbers, but don't worry. Out of all these parameters, the one we care about is QTS. For horn speaker designs, you need a driver with a QTS value lower than 0.4. I've selected this driver here, and all the required information is available in its spec sheet. Ignore the rest of the parameters for now, you don't need to worry about them. Next, download Hornresp. I've included the link in the video description. Once you've opened the software, you'll see many input fields, but we only need to focus on a few of them, these ones. Click Add, then double-click on the cell. Now, enter all the driver parameters here like this. If Pmax and Xmax are not listed in the specifications, you can omit them. The radius of the horn throat is determined by the driver's radius, including both the cone and the surround foam. Hornresp requires the cross-sectional area of the horn throat, which you can calculate using this simple formula. Next, calculate the volume of the rear chamber, the box behind the horn, using this experimental formula. You just need to set the horn's cutoff frequency, or FC. That's where the horn starts doing its job. The other parameters are already in the speaker's specs. Make sure to choose a cutoff frequency that doesn't result in a box that's too small. For example, 83 Hz. The volume of the rear box was calculated to be 3.6 liters. Set all of these cells to 0 first. Multiply 3.6 by 100, then choose a suitable box width to fit your driver. 15 is a good value. After that, set the box height, for example 24. And finally, enter the depth here. Take note of all the numbers you've entered. Make sure to select for pi for this cell. Now, enter random values in these cells. Don't worry, we'll adjust them later. Keep double-clicking on this cell until it shows EXP. Once it does, double-click here to open its related settings window. Now, enter your chosen cutoff frequency, then click on Calculate. Save your project for now so you can see what happens next. This is the calculated horn profile, including the rear chamber. The acoustical impedance chart gives you an idea of the horn's activity. These sharp peaks indicate that the horn produces harsh and uneven sound at those frequencies, which isn't pleasant to hear. You can also observe this on the acoustic power chart. What you want is a smooth curve like this one. Now, take a look at CIR. If we increase the cross-sectional area of the horn mouth, the CIR value will also increase. A value close to 1 gives you a horn with minimal peaks and a smoother sound response. Keep in mind, the larger the horn mouth, the longer the horn needs to be. In this case, the horn length is about 1.6 meters. To deal with this, you can try other types of horns that expand more quickly. I've explained those in detail in other videos on this channel. The peaks have disappeared. This is the horn's directivity response. If you compare it with a direct radiator or speaker without a horn, you'll notice how the horn focuses the sound in a specific direction. This concentration reduces room reflections and results in a more natural sound. Now, we need to export the required data points so we can import them into a CAD software. This is the end of part 1. In part 2, we'll model the horn in CAD. First, we'll create the speaker driver. You can use software like Fusion 360, SolidWorks, or Alibre Design. I personally use Alibre because it's lightweight and fast. A 2D sketch is the key to getting the final 3D shape. Select the XY plane and click on Activate 2D Sketch. First, sketch the speaker frame. The dashed lines you see are guidelines. They won't affect the final model. Set the dimensions now so you can refer back to them later. Remove the unnecessary parts. Then, extrude the frame and define its thickness. Next, switch to the YZ plane to draw the cone profile. The radius of the cone is about 55.5 millimeters. These numbers are approximate. Before continuing, save your project in any location you prefer. Now it's time to create the enclosure. We'll need 4 sketches, 1 for the main box volume, and 3 more to create the mounting area for the driver. If you're using the centimeters thick wood, remember to add 4 centimeters to both the width and height of the internal box dimensions. We've created the second sketch so far. Next, create the third one. You can set the depth of the speaker frame to match the driver frame thickness to millimeters, but I made it deeper to make the border between the frame and the box more visible. The box hasn't been hollowed out yet. To do this, create a new plane to remove the inner volume of the enclosure. You need to enter the rear box dimensions from Hornresp here. Now that the box is fully designed, we need to add another plate on the front to mount the horn onto it. In reality, during assembly, you would simply screw the plates together. Here is the horn mounting plate. The final step is to import the horn profile points into the CAD software. This is very simple. The radius and length values are all we need to create the horn profile. Multiply each point by 10 and enter them into the CAD software. For the first point, enter 55.5, the same value we used for the horn throat in the sketch. The value 26 for Z includes both the horn plate and the mounting depth of the driver frame. Select all the points in the YZ plane. Then, use the spline tool to draw the horn profile by connecting the points smoothly. Let's assume the horn wall has a thickness of 2 cm at the start and 0.8 cm at the end. Be sure to draw a closed profile. If the shape is open, you'll get an error like this. Finally, assign colors to the surfaces to make your design easier to visualize. Thanks for watching.